So good day. This is my demo for hands-on lab number 3. So we have the OR NOT combination circuit. So let's first I will just discuss the nature of these gates. So we have first the quad OR gate, and next I'll have my hex inverter, which is the NOT gate. So the nature of the OR gate is that either both inputs must be at logic 1 so that the LED will be at logic 1. But since we have an inverter, any output produced by the OR gate will be inverted by this hex inverter. So whatever output the OR gate produces, it will be will be inverted, and that output by the hex inverter will be reflected in the LED. So we have a truth table over there. So I'll start with my simulation to prove the truth table. So at first we have at both logic 0, the LED is turned on. As you can see from our OR gate that it won't be turned on because it is an OR gate. It must either outputs must be 1. So with the help of this hex inverter, the LED is turned on, is at logic 1, because the output coming from the OR inverter is a 0. So we have this LED at logic 1. Next we have at at 1 0. Switch B is turned on. As you can see from our truth table, the A plus B output, which is passing at the OR gate, will be 1 since it's an OR gate. So when it passes through the hex inverter, it will be flipped. It will be at logic 0 when it reflects at the LED. So we can see that the LED is turned off. So it's also shown at the truth table. So next we have at 1 0. It is the same. The LED is also at logic 0. So at both switches, 1 1, both switches are turned on. It is also at logic 0 because of this hex inverter that inverts the output coming from the OR gate. So as you can see, the truth table, it is equal to this simulation I have. So next I am gonna go to my NOR equivalent circuit. So in this NOR equivalent circuit, I have the quad NOR gate. So the nature of the NOR gate is that if either both A and B, or it can be both A and B that are not true, are not at logic 0, then Q will be at logic 1. So again, if either A and B or both A and B are not true, meaning at logic 0, then Q will be at the output, will be at logic 1. So our truth table is over there, and let's see if this demonstration has verified the truth table. So I'll start. So at logic 0, both switches off at logic 0, we have the output at logic 1. So that is the nature of the NOR gate, that it must either contain a logic 1 in its input, so that it must either contain a logic 0. It must contain it, but it can be both or either of the two are logic 0, so that the Q or the output will be at logic 1. So next we go to The next what it says, we have at 0 0 at 1 0, you can see that the LED is turned off at logic 0. It is also the same when it is at 1 0. It is because that it needs to be both A and B must not be must not are must not be not true or at logic 0, so that the output rather will be at logic 1. So it doesn't contain both of the inputs, both of it's not both inputs that are not true, so the output is at logic 0. It won't turn on. So meanwhile, at both switches turned on, both logic 1, it is still off because as I said, it is the nature of the OR gate that both A and B must not be at logic 1, sorry, so that the LED is true or at logic 1. So the both switches must be logic 0, and that is reflected here in my truth table. So next I'm gonna go to my AND NOT combination circuit, which is similar to the OR NOT combination. We have the AND gate, quad AND gate, and another hex inverter, the NOT gate. So any output being reflected by this AND gate will be inverted when it passes through the NOT gate. So the nature of the AND gate is that both A and B must be turned true, so that the LED, or the output rather, is also true. So it can't be both, it must be both. It can't be just one of them. It must be both of them at logic 1, so that the output is also at logic 1. And then I'm gonna show the simulation to prove my truth table. So at both switches at logic 0, so we can see that LED is at logic 1. It does it with, that is because the presence of the inverter. When it passes through the AND gate, it must be 0, right? Because of the AND nature of the AND gate. So because of, with the help of the hex inverter, the NOT gate, it will be flipped. That 0 output coming from the AND gate will be flipped and will be make the LED at logic 1. So next is at 0 1, it is still at turned on because whatever the output that is being passed by the AND gate, the hex inverter will flip it. So at the normal AND gate, the LED usually won't turn on, but since there is an inverter, the LED is at logic 1. So next we have at 1 0, still the LED is turned on. And at both switches at logic 1, the LED is now at logic 0, and that's because of the inverter. It inverts whatever output coming. So normally at the AND gate, it must be both at logic 1 so that the LED is at logic 1. Now it's the opposite because of the hex inverter. The LED is at logic 0. So I'll proceed to my equivalent NAND gate. So by using the NAND gate IC, we have our equivalent circuit. So the nature of the NAND gate is that if both A and B are true, then the output is not true. It means that if both A and B are at logic 1, then the output will be at logic 0. So let's see if it matches the truth table. I'll verify in this simulation. At both A at both logic 0, both switches are turned off. The output is at logic 1. And that is because of the nature of the NAND gate, that both of them must be at logic 1 so that this LED will not turn on. It must be both. So let's move on to the next part. The table at 0, 1 still turned on because as I said, both must be turned at logic 1. Still turned on at 1, 0. The LED is at logic 1. So now we have both switches at logic 1. We have met the condition of the NAND gate, and that will lead to LED becoming logic 0, that it is off, because that is the nature of the NAND gate. Both A and B must be at logic 1 so that their output is not true or at logic 0. So that it is the same. I have proven that the outputs are the same in both of my tables. So that concludes my demonstration and thank you for watching.